Welcome to section 15.7. In this section, we're going to be continuing our work with triple integrals, but we're going to start looking at them through the lens of a different coordinate system. So we're going to start talking about the concept of cylindrical coordinates. Cylindrical coordinates are going to be very, very similar to polar coordinates. So we have some of the same conversions from polar coordinates that we have seen before. In cylindrical coordinates, we're dealing in 3D now. So polar coordinates was always just x's and y's turning into r's and thetas. But in cylindrical coordinates, we also have a z component. So we're going to have an ordered triple r theta z. Basically, the way that I describe cylindrical coordinates, it's just polar with a z. So if we want to describe a point in 3 space, we could use rectangular coordinates, right? Cartesian coordinates, what we're used to with x, y, and z. Or we could use polar for the 2-dimensional portion and then go up with the z. So you can see over here, r is giving us that distance away from the origin. Theta is telling us how far around to go. And then z tells us how far up to go in order to get to a point in 3 space. So consider fixing r, letting theta and z be unrestricted. So picture what would happen if we let z be anything, so as far up and down as we want. Theta can be anything, so we can go around and around and around as much as we want. And r is fixed at this one specific value. What you create is a cylinder. So hence the name cylindrical coordinates. So we're really just employing the techniques of polar coordinates to 3 dimensions now. So to start us off, before we get into the calculus of this, just a little bit of practice with the conversions here. Because it is just polar with a z, but I know it can get a little messy when you see 3 components or 3 coordinates here. So let's try a couple examples. For part A, plot the point with cylindrical coordinates 2 pi over 3, and 1, and find its rectangular coordinates. So for the 3D graphing portion, so we've got x, y, z. So 2, that's like our r value. That tells us how far out to go. So say that that's 2 units right there. Theta, 2 pi over 3, tells us how far around to go. So we start at the positive x-axis. That's this way. So, right, if you're picturing the unit circle down here, this is where the angle 0 starts, and then we go around this way. So we start here, and we're going 2 pi over 3. So that's going to be, that's like 4 pi over 6. So just above pi over 2. So we're going to go to right about there. Okay, so r equals 2 tells us how far out. Theta equals 2 pi over 3 tells us how far around. Okay, so you can see if I just transfer r over there, it gets us to that point. And then z is 1, telling us to go up, just straight up 1 unit, which is going to be right around there. Okay. So that would be our point in question. Now, if we wanted to find this point in rectangular coordinates, we can just use our polar conversions. So x is going to be 2 cosine of 2 pi over 3. Cosine of 2 pi over 3 is negative 1/2, so we get negative 1. y is 2 sine of 2 pi over 3. Sine of 2 pi over 3 is root 3 over 2. So we get just root 3. And z is the nice and easy part in cylindrical coordinates because it's just 1 and it's already been given to us. So we get -1, rad 3, 1 are the coordinates of the point in rectangular coordinates, which, different color here, if we were to go -1 this way, root 3 is a little bit bigger than 1, so there's -1 that way. Oops. And then a little bit bigger than 1 this way, and then 1 this way. And that would get us to the same point using rectangular coordinates. So this is the same point written both ways. Now, we can also convert the other direction. So if we're given a point 3, -3, -7, and we're asked to convert to cylindrical coordinates, we need r, theta, and z. The z is always the easy one. R is also usually pretty simple because we know that r squared is equal to x squared plus y squared from our conversion formulas. So r squared is 9 plus 9 is 18. So r, that would simplify to 3 rad 2. So we get r is 3 rad 2. For theta, you can really use any of these angular conversions, but we need to take note of where this angle will be. So let me use the tangent one, and I'll explain why in just a second. But we know that tangent of theta is y over x, so that's -3 over 3, which is -1. So we're looking for the angle that makes tangent -1. This is where sine and cosine, or the x and the y, have the same value, but one is negative and one is positive. So we know that that's going to be at one of the multiples of pi over 4, right? That would be pi over 4, 3 pi over 4, 5 pi over 4, or 7 pi over 4. Right, one of those 4 angles on the unit circle. What we know about this is that the y value, which is the sine value, is negative, and the cosine value, which is the x value, is positive. So we have a positive x puts us over here, and a negative y puts us down here. So it has to be this angle. So that's 7 pi over 4. So again, you can do the conversion with just sine or just cosine, but you have to take them both into account to know which angle it actually will be. So that's theta. And of course, z is just a gimme in a problem like this. So z is just -7. So we get 3 rad 2, comma 7 pi over 4, comma -7. Or alternatively, some people don't like to take the full 7 pi over 4 because that angle goes all the way around. They like to sometimes just take the acute angle, the smaller angle between here and the positive x-axis. So they could just go 3 rad 2, comma negative pi over 4, comma -7. That is also an equivalent, acceptable solution. Right. Let's take a look at the concept of surfaces. in cylindrical coordinates. Cylindrical coordinates are useful in problems that involve symmetry about an axis. So, namely, a cylinder, a circular cylinder, x squared plus y squared equals c squared. You can see in the graph right here. This graph, if you can see down here in the xy plane, we've got this circle right here with, I've got these points labeled on there. So if we look in cylindrical coordinates, excuse me, in cylindrical coordinates, this is r squared equals c squared, which is just r equals c. So this would be the equation of the cylinder. And we can see, of course, right, on this circle right here, it's just whatever this radius is. So that would be, right, C 0, 0. This one would be 0, C 0, like that. So that's what defines our cylinder, is simply one constant radius value and then unrestricted z and theta values. Let's look at an example right here. Describe the surface whose equation in cylindrical coordinates is z equals r. So this one's a little bit different because back up here we had r equals c, so r was equal to a constant. Here we have a variable z and a variable r that are equal to each other for any value. So important thing to notice here, because z represents the height on the surface and r represents the radius of the surface, this means that their height and radius are always the same. All right? This surface, the height and the radius will always be the same. Okay, so as we go out farther on the radius, we go up higher on the surface. Okay. Notice in this equation that theta is not present. So it is unrestricted, or in other words, it can be anything. Okay, so theta is not in the equation, meaning theta can be anything. So we're going all the way around these circular shapes. If we look at level curves for this surface, that would give us z equals, that would give us, it's z equals r, but then we get r equals k because we're setting it equal to a constant. And r equals k are circles of radius k. So we would have, right, if k is 0, then r is 0. If k is 1, r is 1. If k is 2, r is 2. And then et cetera, et cetera, et cetera. So we just get concentric circles all centered around the origin. So we have a circular shape that it seems to be evenly spaced, right, as it's going up. The radius, width, and the height are the same at every point, and theta is going all the way around the entire circle. If we put those level curves, those contours onto, if we project them up onto the surface, we get something that looks like this. So you can see those circles project up, and you can see the surface that we have here is a circular cone. Right? Both the plus case and the minus case, because these cones are two-sided. So we've looked at plotting points in cylindrical coordinates. We've looked at surfaces in cylindrical coordinates. Now we're going to take a look at evaluating integrals. So evaluating triple integrals with cylindrical coordinates. So suppose that E is a type 1 region, so projecting down onto the xy plane. So this projection D onto the xy plane is described in polar coordinates. So we have x and y are in the domain. Z is between two functions of x and y. But then this region D is best described using r and theta. In that case, the 3D component stays z, and the 2D double integral that goes along with it will just be in polar instead of x's and y's. So here's the conversion formula right here. So I have it pre-written because it's kind of long for you to sit here and watch me write it all out. But we have the triple integral over E of f of x, y, z dv. We take the 3D portion first, right? That 3D, the z integral here. And then that will all convert into r's, thetas, and z's. So we have the dz integral right here. So we have all the x's become r cosine thetas, all the y's become r sine thetas, and they did up here and down here as well. We include the r, right, because of like r dr d theta, but we can include the r in the first step here. Then we move out to the second one, dr, goes from h1 to h2, okay, two functions of theta, and then we go out to theta, and it goes between alpha and beta. Okay, so we have a triple integral going dz, dr, d theta. And this is going to be our standard setup for triple integrals in cylindrical coordinates. So let's try out an example. A solid E lies within the cylinder x squared plus y squared equals 1, below the plane z equals 4, and above the paraboloid z equals 1 minus x squared minus y squared. Find the volume of E. So if you can see here, it's kind of tucked away behind the green here, but you can see this surface down there. That's the paraboloid down in there. So we formed a surface down here. The plane is up here, right? It's cutting off the top. That's z equals 4. And then the cylinder is going around it right now. So we're looking to find the volume of that solid in there. So the volume of E, that's going to be triple integral over E of 1 dV. So recall, finding the volume of something using triple integrals just involves taking the triple integral of 1. So if we set up our region, so we know we're going to convert this into cylindrical. So r dz, dr, d theta. Z, going from bottom to top, goes from the paraboloid up to the plane at 4, right? So this is z equals 1 minus x squared minus y squared. Or if we convert to polar, just 1 minus r squared. So 1 minus r squared up to 4. And then the dr d theta, this is all being evaluated over a circle, right? A circular disk, going from 0 out to this outermost radius, which is 1, right? That's where the cylinder is. So 0 to 1 for the radius, and we go all the way around. So theta goes 0 to 2 pi. So we can handle the 3D component first. So with respect to z, this is just rz from 1 minus r squared to 4. dr d theta, still out there. So that gives us 4r minus r plus r squared. So let me just rewrite that then. That's going to be just 3r plus r squared dr d theta, 0 to 1, 0 to 2 pi. And everything else from there on out is just a standard double integral in polar coordinates, so I'm going to leave that up to you. But you should get out 7 pi over 2. Okay. You can absolutely apply the theta trick here. And then at that point, you're really just integrating a single integral in terms of r, and then just multiplying it by 2 pi. So that's pretty nice. All right, so that is the volume of that solid found using cylindrical coordinates. Let's take a look at this next example. Evaluate this triple integral that is already given with full bounds in terms of x, y, and z. So if we want to identify what this is, we need to look at the bounds. Because this integrand function, this doesn't tell us anything about the surface or the solid. That's what these do. So z is going from square root of x squared plus y squared up to 2. Okay, so we have z going from square root of x squared plus y squared up to 2. Okay, actually, let me write this a little more formally here. So our solid E is the set of all points x, y, z, such that z is between these two, y is between these two, and x is between -2 and 2. So if we look at the 2D portion first, so the x and the y, this equation, if you square all sides of this, you're going to get y squared equals 4 minus x squared. Add the x squared over, you get x squared plus y squared equals 4. So really what this is just the top half and the bottom half of a circle. And then x is setting the radius of that circle, which is 2. Okay, so this, the projection in the xy plane is a circular disk x squared plus y squared less than or equal to 4. Then for the 3D portion of this, this bottom surface, so z equals square root of x squared plus y squared, this is the equation of a cone, a circular cone. Okay, and right, if you converted this, this would be z equals square root of r squared, or just z equals r, which we just saw a little while ago as the equation of a cone. And then z equals 2, of course, is just a plane. So we're going between a cone and a plane, and we're above a circular disk. So I have the diagram right here. Okay, so here's our cone, here's our plane, and we are looking at the region between the two of them, so the region that's bounded in here, and then our projection down here on that circular disk. So what we want to do here is convert our triple integral of x squared plus y squared dv. So instead of dz, dy, dx, we want to convert this into cylindrical. So we're going to set up triple integral x squared plus y squared is r squared, and then r dz, dr, d theta. So now for the 3D portion, we go from cone up to plane. So that's going to be from z equals r to z equals 2. And then dr and d theta, r goes from 0 out to the edge of that circular disk of radius 2, so 0 to 2. Theta goes 0 to 2 pi, because we're going all the way around. All right. So if we knock out this first part, that's going to be r cubed times z, evaluated from r to 2, dr d theta. So that's going to be 2r cubed minus r to the 4th, dr d theta. Same idea here. You can use the theta trick. You can solve. It's just a pretty straightforward polynomial. So we should get 16 pi over 5 for this one. So a lot of time the calculation and the conversion come down to our ability to understand and potentially visualize the surface that's being described. So just like in a double integral, we want to recognize that this is a circular disk. And then this one, we just need to recognize that it's between a cone and a plane. Even if you didn't know that this was a cone, that doesn't really matter because you can still convert it to polar and then still substitute it in the right spot. So you really don't even need to know what those 3D surfaces are in order to be able to solve for them and convert with them. It just makes it a little easier to visualize if you know what it is. But again, the conversion is not dependent on that. So as long as you know your polar conversions, then that should still work out just fine. Right. But that brings us to the end of section 15.7 and our introduction into cylindrical coordinates. When we come back in the next section, we're going to be looking at an entirely different coordinate system that'll have some similarities to this, but it's going to be pretty different, pretty new. Hopefully that'll be pretty exciting. So I will talk to you all very soon in the next one.